Greetings, ladies and gentlemen. We're looking at another area under the curve problem where I specifically want to find the area from 2 to 4 of the function x cubed. All right, so that's what I'm looking for, and the issue here is that the value of a is not 0. And what happens in that situation is that my x sub I ends up being a binomial, and when I calculate f of x sub I, I'm going to have to cube a binomial, resulting in some ginormous expansion. So it's actually beneficial to us to have our x sub I be a monomial if possible. So what I end up doing here, bless you, is I break this up into from 0 to b of x cubed dx, and I subtract from 0 to a of x cubed dx. Right? So I'll find the entire area from 0 to 4, and I'll subtract the scrap area from 0 to 2, giving me the area from 2 to 4, which is what I wanted in the first place. So I'll classify this as part A, and this as part B. Not the same A and B I was referring to, but part A, I'm going to have to do an entire integral problem. Then part B, I'll have to do an entire integral problem, and I'll subtract their areas in the end. So I'll do the best I can to cover what I can. Here we go. So for part A, let's label some of our variables. So A in part A is 0, B is 4, f of x is x cubed. We could find delta x will be 4 minus 0 over n, right? Or 4 over n. X sub I is going to be a, which fortunately is 0. Wonderful. Wonderful.
Wonderful weather we're having.
Indeed.
We're
not having
Mr.
wonderful
Waddy,
weather.
are you basing this on number 15?
Ish. Yeah, it's related to that. This is example 2 from your Libro.
Okay.
Plus I times delta x, so 4 over n. And as a result, my x sub I, because a was 0, I end up just getting 4i over n, which is much easier to cube when I calculate my f of x sub I than if I had like 1 plus that or 2 plus that, right? Right. Well, this is easier to cube because I can just distribute it over multiplication and division, whereas if I had a plus sign and I had to cube this, I'd have to expand it using a binomial theorem, which I would have not much fun doing that. So this is going to be the limit of the sigma. Let's see, the limit as n goes to infinity of the sigma of I equals 1 to n of f of x sub I cubed, so that is 4i over n cubed times delta x for n. Okay? So the limit of the sigma, lime, of, this is going to be 4 cubed. What's that, 64? I guess I'll show one more step here. 64i cubed over n cubed, right? Multiplied by 4 over n, which is going to equal the limit of the sigma of, what's 64 times 4? Is that 256?
Yeah.
I cubed over n to the 4th. Okay, so now when I actually expand this out, this will be the limit of the sigma. Actually, no more sigma because I'm taking the sigma here. Would be 256 times 1 cubed over n to the 4th plus 256 times 2 cubed over n to the 4th plus ... 256 times n cubed over n to the 4th. All right, and the way I deal with that is I will factor out whatever I can possible, which it looks like each of these terms has a 256, and each of them are divided by n to the 4th. So I'll be able to very nicely factor out a 256 over n to the 4th, leaving me 1 cubed plus 2 cubed plus ... all the way to n cubed. So that's ellipsis there, right? And then I can look up my formula, which is on page 962, is also in yesterday's video. video 256 over n to the 4th times, and I look up my cube formula, and it is n squared times n plus 1 all squared over 4. And now I can cancel out some stuff nicely. N squared cancels out with this partially, leaving 2. 4 cancels out with that, leaving 64 apparently. And I get the limits of, let's see, n plus 1 all squared. I'm going to have to use binomial expansion there. So that'll be 64 times n squared plus 2n plus 1 using a pattern all over n squared equals the limit of 64n squared plus 128n plus 64 over n squared. And then you guys would, as limit experts that you are, at least when limits approach infinity, you would say, oh, we could divide everything here by n squareds, and we'd get the limit of 64 plus 128 over n plus 64 over n squared all over 1. And when I take that limit, this 64 over 1, yeah, I get an area of 64. Okay.
Question.
Yes.
Since we're pros at limit, do we have to do the showing you that it's 128 divided by n and 64 divided by n, or can we just say based on that the ones that are going to end up with n are the 100?
I mean, in this case, because it's a tie between the leading degree, yeah, I'm fine if you use the ratios of that rule. That's fine. Yep.
And do we have to write out that pattern every time for the 256i cubed?
This pattern?
Yeah.
You maybe could skip that. Well, you could skip this step and immediately get to that one. So I'm fine if you jump over this step to this one. Yeah. Because I think you could spot the 1 cubed, 2 cubed, n cubed without having to write it all out again. So I'm fine with that. I mean, for the sake of the video, I kind of like being able to show all of the steps for people following along. Let's see, part B. If the bell rings or we're dismissed by the time I'm done or in the middle of part B, I'm going to keep going for the sake of the video, but your Terea's on the board, so you know what to do. So I'm going from 0 to 2. 0 to 2. So 0 to 2 of x cubed dx. So in this case, cruising right along, a is 0, b is 2. Delta x is going to be 2 over n. X sub I is going to be 0 plus I times 2 over n, or 2i over n. So I'm just going to cruise right along. You might not even have time to write this all down. That's fine. So the limit as n goes to infinity of the sigma as I goes from 1 to n of f of xi, so that's 2i over n cubed, times delta x, which is 2 over n. So this is literally my width times my height. I'm calculating the areas of rectangles, adding them all together, taking the limit as n goes to infinity, so the number of rectangles approaches infinity, and I'm trying to find the area under this curve, and I truly do. So 2 cubed is 8. Oh, might as well write my lime. Lime of 8i cubed over n cubed times 2 over n. So that's going to equal lime in the coconut. Yeah, we'll see. I'm going to do my best. That clock's also fast. I cubed. I might be able to beat the clock. Here we go. So equals that. I can now expand the sigma, right? So that's going to equal, that means 16 times 1 cubed over n to the 4th plus 16 times 2 cubed over n to the 4th plus ... 16 times n cubed over n to the 4th. Right? That's what that limit means. So, using the pattern, limit of the, well, no more sigma, I can factor out a 16 n to the 4th multiplied by the pattern of 1 cubed, 2 cubed, n cubed. It happens to be the same one from the previous one, n squared times n plus 1 all squared all over 4. I believe. Yep. So this is going to equal, let's cancel some stuff out, n squared, bam, 2. Fortunately, most of the math is kind of similar to the previous. Yep. Here we go. Moving right along. 4 times n squared plus 2. Oh, I forgot my limit. Limit of 4 times n squared plus 2n plus 1. Expanding that binomial all over n squared equals limit of 4n squared plus 8n plus 4 all over n squared. And I think you guys agree that that limit is going to equal 4. So the answer to my final question is going to be what minus 4? 64 minus 4. So the area is 60. Yep. So thank you, Internet friends, for watching. And have a great day, Internet friends.